Hi everyone, welcome to the class. In the last class, I was explaining about the calculation of thermodynamic parameters using simple lattice model. As we came to know that the simple lattice model was based on a lot of assumptions which we cannot use for real solutions like polymer solutions. So to overcome the drawbacks of simple lattice model, we are considering Flory Huggins theory. So in this session, I am going to explain about the Flory Huggins theory and how to calculate the entropy change of mixing of polymer solution using Flory Huggins theory. Now let us consider Flory Huggins theory. Flory Huggins theory is also called modified lattice model, and it was proposed independently by Paul Flory and Maurice Huggins in 1940s. This theory explains the miscibility of a polymer with a given solvent, and it is based on the lattice chain model of the polymer solvent system. In this model, the segments of polymer and solvent molecules are shown as points in the lattice. Now let us consider what are the assumptions of Flory Huggins theory. The first one, polymer molecules are much larger as compared to solvent molecules. So Flory Huggins theory considers that the size of a polymer molecule is larger when compared to the size of solvent molecules. And the second assumption, polymer molecule is in the form of a long chain having large number of segments. See, if you consider this polymer molecule, it is made up of a large number of segments. So these segments you may consider it as a repeating unit of the polymer chain. So in this schematic diagram, so this yellow dot represents the solvent molecule and this red dot represents the segment of a polymer chain. And the next assumption is size of solvent molecule is comparable to size of one segment of a polymer chain. So it is a very important assumption when we compare with the simple lattice model. So in case of Flory Huggins theory, we are considering that the size of a solvent molecule is comparable to a size of one segment in a polymer chain. But in case of simple lattice model, we have considered that the size of a polymer molecule itself is equal to a size of a solvent molecule. And the next assumption is each space in a lattice is occupied by either one solvent molecule or a segment of polymer. See, if you consider the crystal lattice, each lattice point is occupied either by the solvent molecule or by the one segment of a polymer. See, lattice site is not occupied by entire polymer molecule. This lattice site is occupied by one segment of a polymer or one repeating unit of a polymer. Each site occupied by polymer segment must have two adjacent polymer sites so that there is a continuous path of polymer segment. See, while adding a polymer segment to the lattice point, we should have to take care of that. So each segment should have two adjacent polymer site because the chain has to grow. Then the solvent molecule and the polymer segment are capable of exchanging sites such that delta H is equal to 0. That means if the polymer segment exchanges the site with the solvent molecule, then that exchange will be athermal. That is, change in enthalpy of the reaction must be a 0. Now we shall consider this Flory Huggins theory to calculate the change in entropy of mixing. Now you consider the crystal lattice, where the lattice points are being occupied by either solvent molecules or the segments of a polymer chain. Suppose number of solvent molecules is represented by N1, that is, there are N1 solvent molecules are present in the crystal lattice. Then the number of polymer molecules be N2 if there are N2 number of polymer molecules. It means, see, if you consider this crystal lattice, you may find this is one polymeric chain, this is another polymeric chain, and this is one more polymeric chain. Like this, there are N2 number of polymer molecules in the crystal lattice. Then number of segments in each polymer molecule is X. This is important. See, each polymer molecule is made up of certain number of repeating units, or we may call it a certain number of segments. Let us consider the number of segments in each polymer molecule be X. Then the total number of segments which are present in the crystal lattice will be equal to X into N2. The total number of sites in a lattice, it can be represented by N0, that will be equal to number of solvent molecules and total number of segment present in the crystal lattice, that is N1 plus X into N2. If the number of chain segments is related to size ratio, then it will be mathematically represented like this. So X, that is number of segments, that will be equal to V2 divided by V1, where V2 and V1 are partial molar volumes of polymer molecule and solvent molecule respectively. Now, as I mentioned earlier, there are N2 number of polymer molecules in a crystal lattice. So, the number of ways of arranging N2 number of polymer molecules in the lattice is given by a thermodynamic probability Wp. To calculate the value of Wp, you just consider the addition of N2 number of polymer molecules one by one, followed by the addition of N1 solvent molecules. That means you consider the crystal lattice. First, we have to add N2 number of polymer molecules into this crystal lattice or into the lattice site of a crystal lattice one by one like this. See, first I am adding one polymer molecule, and then I am adding another polymer molecule, then I am adding one more polymer molecule. As all the N2 number of polymer molecules being added to the crystal lattice, then we have to add the solvent molecules. Now, to calculate the entropy change of mixing of polymer solutions, you just consider, let I number of polymer molecules be initially placed on an empty lattice. You just consider a crystal lattice to which we have already added I number of polymer molecules. Actually, it is not visible to us now. You just imagine we have added I number of polymer molecules already. Then Ix is the number of cells already occupied by the polymer segments. As I have added I number of polymer molecules, each are having X number of segment, then Ix will be the cells which are already occupied by polymer segments. Now, N0 minus Ix is the number of vacant cells available. So, this is the number of vacant cells available in the crystal lattice after adding I number of polymer molecules. Now, determine the number of ways that the I plus first polymer molecule can be placed in the lattice, and it can be done by the successive addition of all the segments of I plus first polymeric molecule. Let us consider the placement of first segment of polymer, that is I plus first polymer. So the number of vacant sites available for this will be N0 minus Ix. So the first polymeric segment can be added in N0 minus Ix number of vacant sites. Now you consider the placement of second segment of a polymeric chain I plus first polymeric chain. So the number of vacant site available for this will be Z into N0 minus Ix divided by N0, where Z is the coordination number. So here you just consider the second segment of a polymer molecule cannot be placed anywhere in the crystal lattice. So it should be placed in adjacent to the first segment because the polymeric chain has to grow. So the number of lattice points available for the placement of second segment of a polymer around the first segment will be denoted by Z, that is coordination number. So we can place the second segment over here or here or here or here. So I just consider we are placing the second segment over here. Now you consider the placement of third segment and all other segments of polymer molecule, that is I plus first polymeric molecule. It can be done in the vacant sites denoted by Z minus 1 into N0 minus Ix divided by N0. So if you look at the placement of second segment, so the available sites are Z into N0 minus Ix divided by N0. That is, this is the probability factor and this is the coordination number. But in case of third segment and all other segments, the vacant site is Z minus 1 into the probability factor N0 minus Ix divided by N0. So this is because while we are adding the second segment in adjacent to the first segment, all the sites around the first segment are free to occupied by the second segment. But whereas in the case of addition of third segment and all other segments, the sites which are present around the previous segment are not free. One of the site is already occupied by the segment. So the number of possibilities will reduce to Z minus 1. That's why here we are considering Z minus 1 into the probability factor. So this is the important point to be considered here. Thus, the I plus first polymer molecule may be placed on a lattice already containing I molecules in Wi plus 1 ways. So this is the thermodynamic probability in which the I plus first polymeric chain can be added to the crystal lattice which is already having I number of molecules of polymer. So which can be mathematically represented like this. So Wi plus 1, it will be equal to, see, this is the probability of adding first segment of I plus first polymeric molecule. This is for the second segment and this term is for the third and remaining segments of a polymeric chain. Now you try to simplify this equation. So Wi plus 1, that is equal to N0 minus Ix, you keep as it is. Then there is a term Z here, then there is Z minus 1 to the power X minus 2. The value of Z is large, hence we can consider this Z as Z minus 1 itself. So on simplifying these two, you will get Z minus 1 to the power X minus 1. Here it is N0 minus Ix divided by N0. Here N0 minus Ix divided by N0 to the power X minus 2. On simplifying these two, we will get N0 minus Ix divided by N0 to the power X minus 1. In this equation, there is N0 minus Ix to the power 1 and N0 minus Ix to the power X minus 1. On simplifying these two, we will get N0 minus Ix to the power X and here Z minus 1 to the power X minus 1. Here 1 over N0 to the power x minus 1. So on simplifying these two or on combining these two, we will get z minus 1 divided by n naught whole to the power x minus 1. This is the probability for the addition of I plus first polymeric chain to the crystal lattice. Then what is the probability for the addition of I number of polymeric chain in a crystal lattice? So that should be equal to n naught minus, here it is Ix, it is for the I plus first polymeric chain. If I consider ith polymeric chain, then this I will become I minus 1 into x whole to the power x into z minus 1 divided by n naught whole to the power x minus 1. Now you consider the total number of ways the polymers can be placed in the lattice, and it is represented as W1, W2, W3, then Wi. That means the thermodynamic probability of adding the first polymeric chain, second polymeric chain, third polymeric chain, like that the ith polymeric chain, as we are having n2 number of polymeric chains, so it should be Wn2. So it is equal to a summation of Wi from I is equal to 1 to n2. By mean field approximation, the number of distinguishable ways in which all the n2 number of polymer molecules can be placed is given by Wp is equal to 1 divided by n2 factorial and summation of Wi from I is equal to 1 to n2. Then you substitute the value of Wi here, you will get this expression. Then on simplification, you will get this equation, that is Wp is equal to n naught factorial divided by n1 factorial into n2 factorial into z minus 1 divided by n naught to the power n2 into x minus 1. This is the number of distinguishable ways in which the polymer molecules can be placed in a crystal lattice. Then the number of distinguishable ways by which the solvent molecule can be placed will be equal to 1, because all the solvent molecules are identical. The exchanging of place will not produce any noticeable changes. Then the total number of ways we can place both the polymer molecules and solvent molecules in the lattice is Wp only. Then according to Boltzmann thermodynamical statistics, this Sm, that is entropy of mixing, that will be equal to K into natural logarithm of Wp. Now you substitute the value of Wp in this equation. So you will get this expression. On simplification, you will get this equation for entropy of mixing. Now you consider entropy of the pure solvent, that is indicated by S1, it is 0. Then for the pure polymer, the value of N1 is equal to 0, because there are no solvent molecules in a pure polymer. Then the entropy for the pure polymer can be obtained by replacing N1 is equal to 0 in this expression, and it will be like this. Entropy of the pure polymer, that is S2, it will be equal to K into N2 into x minus 1 natural logarithm of z minus 1 divided by n0. Now you consider the change in entropy of mixing, that is delta Sm, that will be equal to entropy of the mixture minus entropy of solvent minus entropy of polymer, that is pure polymer. So you substitute the values. So I have substituted the value of entropy of mixture minus the entropy of solvent is 0, then minus S2. So the value of entropy of pure polymer was substituted. So in this equation, the last two terms are same with opposite sign, because here it is minus. When I multiply this one with this minus, it will convert into a plus. Then these are the same terms with opposite sign, they get cancel one another. Then delta Sm, that will be equal to minus k into n1 natural logarithm of n1 divided by n1 plus x into n2 plus n2 natural logarithm of x into n2 divided by n1 plus x n2. Then delta Sm, that is equal to minus k into n1 into natural logarithm of phi 1 plus n2 into natural logarithm of phi 2, where phi 1 and phi 2 are volume fractions of the solvent and polymer respectively. Then this equation, in this equation, n1 is the number of solvent molecules and n2 is the number of polymer molecules. So we can change it into a number of moles of solvent molecules and number of moles of polymer molecules. So in that case, this K will be changes to R. So this is the equation used to calculate the entropy change of mixing of a polymer solution in accordance with the Flory Huggins theory. Well, so far I have explained about the Flory Huggins theory, that is the assumptions of Flory Huggins theory, and how to use the Flory Huggins theory to get an expression for change in entropy of mixing of polymer solution. Hope you understood them. Thank you very much.